The AI era has fully arrived, with applications moving from the cloud to the edge. The development of AI has driven the demand for high computing power and low-latency memory. But what if the memory in AI chips fails? How can we investigate the root cause of the defects? Hey everyone, welcome back to iST channel. I'm your host today, Gloria. To receive the latest news and professional insights about the semiconductor industry, make sure to subscribe so you won't miss any of our videos. Memory devices are categorized into two types. The first type is non-volatile memory, such as flash, is used for long-term storage. The second type is volatile memory, including DRAM and SRAM, temporarily stores data for high-speed computation. You might be more familiar with DRAM, as SRAM is more costly than DRAM and faces challenges in scaling down the process. However, SRAM has advantages like high speed, low latency, and low power consumption. These features make it essential for the high-efficiency computing and machine learning required in AI development. To enhance processor performance, SRAM is stacked in small chips onto CPUs. Within ICs, there are numerous densely packed SRAM structures. Once a failure occurs, whether identifying the abnormal location or analyzing the defect point, both tasks become challenging. In today's video, we will introduce 6 common SRAM failure modes and explain the methods for failure analysis. If you encounter unresolved memory defect issues, be sure to watch until the end. Since failure modes are closely related to the structure of SRAM, let's start with a brief introduction to how SRAM works. A single-bit SRAM is like a small room used to store information as 0 or 1. This small room is composed of 6, 8, or 10 transistors, sometimes even more. The most common type is 6T SRAM. Now that we've introduced the structure of SRAM, we can categorize SRAM failure conditions based on where anomalies appear into the following 6 common modes: single-bit failure, twin-bit failure, quad-bit failure, partial bit line failure, word line failure, and block failure. Before performing failure analysis, iST recommends to first identify the type of failure mode to speed up the analysis process and quickly pinpoint the issue. Next, we invite Bernie, an expert from our failure analysis lab, to explain the methods for analyzing SRAM failure modes.
Hello everyone, I'm Bernie. We'll explain the failure modes and solutions from the smallest to the largest range of failure. First, let's talk about single-bit failure. Single-bit failure can actually be grouped into 2 types: soft single-bit failure, which only fails to operate under specific operation voltages, and hard single-bit, which fails to operate under any operation voltage. When a single bit fails, we first delayer the sample and mark the location using FIB, then use SEM or CAFM to search for the anomaly point layer by layer. There's also a special case where if no anomalies are found in the metal layer, we use a nano-prober to perform electrical measurements on the PU, PD, or PG components. Here's an example. In this 6T SRAM, since both connected structures are electrical in nature, no defects were observed with SEM or CAFM. This is when the nano-prober comes into play. Through electrical measurement, we discovered that 2 circuit structures that shouldn't be connected were short-circuited. This allowed us to identify the defect's location. Further analysis with FIB or TM to identify any physical anomalies is recommended for root cause improvement. Twin-bit failure involves 2 horizontally or vertically adjacent bits. For both twin-bit and quad-bit failures, the initial steps are the same as for single-bit failure: delayer the sample, mark the location, then use SEM and CAFM to search for defects from the topmost layer of the structure down. Defects in twin-bit failure often occur in the shared circuit structures of the 2 bits. Looking at the twin-bit circuit diagrams on screen, delayering to the highest shared layer of the VIA and observing with SEM will reveal abnormalities in the VC connecting to the word line between the adjacent bits, showing a break in the structure below the defect. Partial bit line failure refers to a situation where some bits on a bit line operate normally while others do not. The fault of such failure mode can be revealed on the bit line circuit at the boundary between the normal and abnormal bits. How do we find the defects? Before delayering for analysis, we use Oberch and NGAS for hotspot positioning for localizing the abnormal areas. Then we proceed with delayering, positioning, and analysis. Bit line failure, word line failure, and block failure are similar, differing mainly in the location and extent of the failure. Bit line failure occurs on the bit line outside the SRAM array. Word line failure follows the same logic, and block failure, as the name suggests, results in the entire block failing due to the anomaly. These three failure modes are related to the peripheral circuits around the SRAM. We can initially use OBERT and NGAS for hotspot positioning, and then delayer based on the hotspot locations. The subsequent analysis is similar to the methods described above. As we've explained, while there are many SRAM failure modes, they are not overly complicated. However, you may have experienced difficulty in pinpointing defects when analyzing SRAM failures. In such cases, we recommend using an alternative verification method, Scramble Check. Scramble Check is mainly used for verification during the early stages of new product development. After discussing with IC designers, specific word lines or bit lines, or even specific bits, are selected first. FIB-IC circuit edit techniques are implemented to cut these lines to create artificial failure locations. With the electrical testing results, we can therefore identify the correlation between electrical address and physical address. After the Scramble Check verification, the possibility of not finding the correct analysis location in SRAM product failure analysis can be eliminated.
The evolution of AI relies on advancements in memory technology. Faster and larger memory capacities can accelerate big data processing and storage, enhancing AI performance and efficiency. For detailed articles on SRAM, please click the link in the comments section. For any questions, feel free to email us or join our official Line account for inquiries. To stay updated, follow us on LinkedIn or Facebook. That's a wrap for today. See you. If you enjoyed our video, don't forget to like, subscribe, and hit the notification bell so you won't miss any updates.